All right, so let's go over some questions from Unit 1, Module 1. Let's start with this question. You have three substances, A, B, and C. You are given the normal boiling points. And then if you are at 300 Kelvin and 1 atm, that is 300 Kelvin is around 27 centigrades, because remember the Kelvin temperature is Celsius plus 273. Therefore, Celsius must be Kelvin minus 273. Okay, so 300 minus 273 is around 27. Okay, and then that temperature, so now the current temperature is below the boiling temperatures of all of them. Okay, so as a result of that, okay, let me have this over here. So we have C, B, and A boiling temperatures over here at 120, 80, and 45. Our temperature is around over here, which is 27. Okay, and because you are below the boiling temperature, just like when you have water, if you are below 100 degrees Celsius, the dominant phase is liquid. So as a result of that, I mean, same thing applies here. Because we are below the boiling temperatures of all of the substances, we should be in the liquid phase. Okay. Now, what does it say? Given the information provided, what is true if you want to separate these substances? No energy will be required to separate them. Energy will have to be provided to the system. So the idea is, if you want to separate them, now all of them are in the liquid phase. What we want to do is we want to we need to have at least one. We need to have one substance in a different phase than the other two. So for us to do that, we need to increase the temperature. For example, if we increase the temperature to over here, then we are above the boiling temperature of A, meaning A is in the gas phase, and then B and C will be still in the liquid phase. And once we're done with that, we can separate B by raising the temperature to around, say, 90 degrees, above 80 degrees Celsius. Okay, so we need to provide energy to the system to separate them. So first option is incorrect. No energy will be required. No. Energy will have to be provided. That is true. More information is needed. No. Energy will have to be extracted from the system. No. If we cool it down, yeah, so they will still be in the liquid phase. I mean, as long as you are above the melting temperature, and then if you go below the melting temperature, all of them will be in the not all of them. Okay, so you will go to the solid phase. Okay, easiest thing to do here is raising the temperature so that we can separate them as liquids and gases. Okay, now let's enter that answer. Moving on. Question 2. Select the change in energy versus temperature curve that corresponds to the process A to B in the phase diagram. Okay, so let's take a picture again. All right, so A to B, so this line over here, this boundary over here is the gas liquid boundary. If you're going from A to B, we are vaporizing. Liquid is becoming a gas. So if that is the case, we are providing energy to the system. We are heating the system, because you see that we are increasing the temperature from A to B. A is at a lower temperature and B is at a higher temperature. And if that is the case, we are providing energy to the system. Therefore, delta E must be greater than 0. Okay. And then I don't see all the graphs here. So what I'm going to do is I'm going to draw my own graph, and then we'll look at what is going on. This is the change in energy, and this is the temperature. We are starting at a lower temperature of TA. And then when we increase the temperature, energy will be absorbed by the system, and therefore the delta E increases linearly. And during the phase transition, which is this region over here, the temperature does not change. All the energy is provided is used to convert the liquid to a gas, to the gas, liquid to the gas phase. And once everything's converted to gas phase, then again, with temperature, the absorbed energy increases like that. So this should be the curve we are looking at. And then we're starting at T0, and then we are delta E0, because that is when we have done nothing to the system. And then we're going to end up at a higher temperature of T. Okay, so it should look like that. Then let's go find that answer. Not that. Yeah, it looks like this one. Right? It cannot be C, because in C you are starting at a higher temperature and ending up at a lower temperature. If you are heating, this cannot happen. All right, so and also anything below 0 is not possible, because if we are heating, delta E is always positive. All right, so let's go with that answer and take a look at this question. Question 3. Select the correct process given by the circle on the delta E versus temperature curve that correspond to the process of C to A. Okay, so C to A, all right, so we are starting at a higher temperature, and then we are ending up at a lower temperature. So our starting point, let me actually do this in a different way. Okay, so we are starting at delta is equal to 0. That's our starting point, because we haven't done anything to the system when delta E, or change in energy, is 0. Okay, and then what we are doing here is we are going, although C to A is our overall process, it seems like we are first going from C to B and then B to A. Okay, anyway, let's see. Now, no, maybe not. Maybe we are going from C to A, C to A directly, because we are decreasing the temperature. So when we decrease the temperature, delta E decreases. And then during the phase transition, which is this point over here, the gas is becoming a liquid. And once everything has become a liquid, then again, when you decrease the temperature, which is this region over here, the temperature decreases, and so does the energy. And and at the phase transition temperature, you see that the temperature is not changing. Let me mark that with yellow at this point. Temperature is not changing, but energy is released from the system to convert the liquid to solid. And then once everything is converted to solid, when the temperature decreases of the solid, the energy also should decrease. Right, so these are the regions. So what is happening here is freezing. Liquid is becoming a solid. Okay. Okay, let's go back and enter that answer. All right, it's freezing, solid and liquid is present. So yeah, they're asking for the phases as well. Select the correct process. By circle, we did that. In the phase diagram of near shell. Okay, it's freezing. All right, so that's the only answer we are having there. Okay, and moving on to question 4, which of the following properties could be best used to differentiate different types of solids at room temperature? It needs to be, to differentiate something, we need to have differentiating characteristics, which are intensive and unique. And the only intensive property I'm seeing here is the melting temperature. So we're going to go with that for sure. And moving on to question 5, we are given wave pressure curve. we are given vapor pressure curves of 3 different substances, and then we are asked to predict or rank the boiling temperatures. Let me use a picture. Okay, so I mean, there are different ways of doing this. So let's say that of a certain 40 Kelvin, I'm sorry, 40 kilopascals. So let me draw the 40 kilopascals line over here. Here's the 40 kilopascals line. Okay, so that is our external temperature, and then acetone will reach 40 kilopascals around, I mean, at the lowest temperature, and then ethanol, and then to boil butanol, for butanol to reach the external pressure of 40 kilopascals. Its temperature needs to be closer to around 380 or something like that, 360 or something like that. So therefore, we have the highest boiling point for butanol, and then it cannot be these answers then. And then the lowest boiling point is for acetone, and that leaves us with option B. Okay, so let's go with that. Moving on, the vapor pressure curves for methanol, water, and isopropanol are shown below. Under what temperature range are methanol, water, and isopropanol in the liquid phase at 20 kilopascals? Okay, let's do it again here. All right, so again, whenever they give you the pressure, what I would do is I would draw the line to indicate the pressure line. So 20 kilopascals is around here, right? And the question is, under what temperature range are methanol, water, and isopropanol are in the liquid phase? Okay, so if you can remember, this vapor pressure curves are liquid gas boundary of the vapor pressure curve. So we have solid, liquid, and gas over here. Okay, so above the curve you're a liquid, and below the curve you're a gas. Okay, so you want to be above the curves with respect to all of them. So you should be in this region. Okay, so that should be below 302 Kelvin. So can it be above? It needs to be below 300. This is 300 over here. It needs to be below this temperature over here. That's what we can select. All right. Moving on. The vapor pressure curve for substances are given, starting at 40 kilopascals and 390 Kelvin. Which strategy would or could be used to separate butanol from acetone and ethanol? All right. So we want to separate butanol, which is the orange curve, from acetone and ethanol. That means butanol should be in a different phase than ethanol and acetone. In other words, we need to be somewhere around here. That's the idea. Okay. So option 1 says decrease the temperature to 350 Kelvin. 350 Kelvin and increase the pressure to 60 kilopascals. So let's mark that point. 350 Kelvin and 60 kilopascals is over here, so it works perfectly. And decrease the temperature to 310 Kelvin while pressure is constant. So we are at 40 Kelvin initially, 40 kilopascals initially. And if you decrease the temperature to 310, you will be over here. It doesn't work. So that is out. You need to be in this blue circle blue region. Option 3, decrease the pressure to 20 kilopascals while decreasing the temperature to 310 Kelvin. So 20 and 310 is around here. Nope, we are not in the blue region over here. If you're not here, we cannot separate butanol from other guys. So that is out as well, one only. Okay. And moving on. Imagine you have substances A, B, and C in a container at -10 and 1 atm. Under these conditions, the system contains, all right, the phase, so -10. So if you want to convert this to Kelvin, let me do this one more time. Kelvin, remember Kelvin, no, the Kelvin temperature is 273 plus Celsius. Okay, so that should be 273 plus -10, which is 263 Kelvin. Okay, so here's the temperature line, right? Here's the boiling point of A, 275, and here's the boiling point of C, 225, and here's the boiling temperature of B, which is 150 Kelvin. Okay, and then your temperature is 263 Kelvin, which is around here. Now, under these conditions, we are below the boiling temperature of A. Therefore, A should be in the liquid phase. And then we are above the boiling temperature of C. Therefore, C should be in the gas phase, and B also should be in the gas phase because we are above the boiling temperature of B. Okay, so we have two gases and one liquid. So should be option 1. Okay. Moving on, the phase diagram for neon is shown below. Estimate the freezing temperature of neon at 10 atm. Okay, one more time. So again, 10 atm, draw the line. Let's draw the line. Okay, so 10 atm is over here. And freezing means liquid is becoming a solid. So we are looking at the liquid solid boundary, which is this boundary over here. Okay, so this is the boundary of interest for us. Okay, now the freezing temperature should be somewhere around here. And then if you estimate that temperature, so that is closer to 20, so 25, 30, it should be around 25 Kelvin. Okay, let's select 25, moving on. Select the temperature versus time curve that correspond to the process of B to A in the phase diagram of neon. All right, so we might have to draw it out before we look at the options. B to A, we are cooling, right? Because B is at a higher temperature around here, and A is at lower temperature, so we are cooling. So that means we are going from a higher temperature to lower temperature, okay? And if that is the case, let me use a different color. If that is the case, here's my temperature axis, here's my time. We're starting at a higher temperature. This is going to be the temperature of B. And then when we cool, the temperature decreases with time. And then during the phase transition temperature, which is over here, okay, the temperature remains constant, but we are still removing energy from the system because we are decreasing the potential energy. And then once everything is converted to a solid, this is okay, this is where, give me a second, liquid is becoming a solid. And once everything has become a solid again, temperature decreases with time until the temperature of point A is reached, because that's the end point of experiment. So, yeah, so it's definitely not what we're looking at here, because here the temperature is decreasing. I mean, without time, you know, I mean, that can never happen. It takes time. Anyway, it needs to look something like what we drew over here. All right, so let's select that. Okay, yeah, that looks like this curve over here. That's it. And let's submit our quiz. Submit. There you go. That's how we get 100% on that quiz. All right. Bye, everybody. I'll see you guys in class.